Hi everybody, welcome to the first video in the derivative section of the Calculus Guide video series. In this video I'm going to talk more about the definition of the derivative, and I'm going to introduce some calculation rules for the derivative. So the first thing I'm going to do is to recap some points from our introduction to calculus videos, and that's that each of these 5 things are the same thing. The slope of y equals f of x at the point x equals x naught, that's the same as the slope of the tangent to the curve y equals f of x at the point x equals x naught. And they're both the same as the rate of change of the function f of x with respect to x at the point x equals x naught. And they're all the same as the derivative of the function f at the point x equals x naught. And they're all the same as the limit of the difference quotient f of x naught plus h minus f of x naught, all divided by h, as h approaches 0. So each of these things are referring to the same thing. If you'd like to revise or to learn more about this, this is covered in more depth in the Introduction to Calculus section of the Calculus Guide video series. In this video, I'll be talking more about the definition of the derivative, and we're going to introduce some calculation rules for the derivative. The derivative is one of the 2 most important mathematical objects in calculus. So far, we've been finding derivatives by evaluating limits. This can be difficult and time-consuming. So, in this section, we're going to learn techniques that make calculating derivatives easier. We're going to learn some calculation rules which allow us to calculate derivatives without having to evaluate limits. So, for the definition of the derivative, up until now, we define the derivative of a function f of x at x naught as the limit of the difference quotient f of x naught plus h minus f of x naught, all divided by h, as h approaches 0. We now define the derivative as a function dy dx, whose value at x is the limit of the difference quotient f of x plus h minus f of x, all divided by h, as h approaches 0, provided that the limit exists. And the domain of the derivative dy dx is the set of points in the domain of f of x for which the limit exists. So now I'm going to introduce some new terms. If the derivative dy dx exists at a value of x, we say that the function f of x is differentiable at that value of x. And the process of calculating a derivative is called differentiation. Here we're going to introduce some information about notation. So, notation refers to how we represent something in writing. And there's a number of different ways to represent the derivative of a function f of x in writing. The common notations are displayed here in this table. Our first notation is written as f apostrophe x. So we read this as f prime x. That's the convention. And this notation is Isaac Newton's notation. Another way to do it is y apostrophe. We read this as y prime. Another notation again is dy divided by dx. So we read this as dy dx, or the derivative of y with respect to x. So this is Leibniz's notation. For the most part, in this material, in an effort to standardize how I do things, I've always made an effort to use Leibniz's notation, and I've occasionally used the df dx notation as well to stay consistent. So another way to write the derivative is df divided by dx. We read that as df dx, or the derivative of f with respect to x. Another way to write it again is d divided by dx f of x. So we read this as d dx of f of x, or the derivative of f with respect to x. So what you're seeing here is that there's lots of different ways to represent the derivative in writing. The main thing to remember here is that all of these written notations, they all represent the same thing. So they all represent the derivative. So depending on what textbook you're using, or what teacher or what tutor you're working with, they might be using, say, one of these notations or another one of the notations. I guess the important thing to remember is that these notations, they're not referring to some different thing. They're all referring to the same thing. They all refer to the derivative. So here we're going to look at an example of calculating the derivative dy dx from the definition of derivative by evaluating a limit. The reason that we're looking at this example is that we're going to see that calculating the derivative by evaluating a limit, it can be less efficient and more time consuming than simply using a calculation rule. So we're going to do it the longer method first, evaluating a limit, and then we're going to introduce some rules, and we're going to see how by using the rules we can evaluate a derivative faster and more efficiently. So if we wanted to calculate a derivative from the definition of derivative by evaluating a limit, these are the three steps that we'd use. Our step one would be to evaluate f of x and f of x plus h. Our step two would be to evaluate and simplify the difference quotient, f of x plus h minus f of x all divided by h. Our step three would be to use the simplified difference quotient and evaluate the limit. So our derivative dy dx is equal to the limit of f of x plus h minus f of x all divided by h as h approaches 0. So here's an example. We want to find the derivative of f of x is equal to x squared. Step 1, our f of x is equal to x squared, and f of x plus h is equal to x plus h squared. For step 2, we evaluate our difference quotients. So our difference quotient is f of x plus h minus f of x all divided by h. Next we substitute in our values for f of x plus h and f of x, and we get x plus h squared minus x squared all divided by h. When we multiply out the x plus h squared term, we get x squared plus 2xh plus h squared minus x squared all divided by h. So our plus x squared and our minus x squared cancel. And on our next line, we get 2xh plus h squared all divided by h. When we divide by h, we get 2x plus h. So our difference quotient has been evaluated and simplified down to 2x plus h. For our step 3, our derivative dy dx is equal to the limit of our simplified difference quotient as h approaches 0. So it's equal to, our derivative is equal to the limit of 2x plus h as h approaches 0. So we can evaluate that limit by substitution. We can simply replace the h with a 0. So our limit evaluates to 2x plus 0, which is equal to 2x. So we've calculated that our derivative dy dx is equal to 2x from the definition of the derivative by evaluating the limit. So finding derivatives by evaluating limits, it can be difficult and it can be a bit time consuming. So now we're going to cover a series of rules for calculating derivatives. And by using these rules, it'll allow us to do it in a more efficient and a less time consuming manner. So our first rule is to calculate the derivatives of constants. The derivative of every constant function is 0. If our function f of x is equal to c, where c is some constant, then our derivative, df dx, is equal to the derivative of c with respect to x, which is equal to 0. As an example, if our function f of x is equal to 5, then our derivative, df dx, is equal to the derivative of 5 with respect to x, which is equal to 0. As another example, if our function f of x is equal to pi, some other constant, then our derivative, df dx, is equal to the derivative of pi with respect to x, which is equal to 0. So if our function is equal to some constant, then the derivative of that function is equal to the derivative of the constant, which is equal to 0. If our function f of x contains terms with x in them, then we would no longer be dealing with a constant, and we wouldn't be able to apply this constant rule. So our second rule is the power rule. If our function f of x is equal to x raised to the power of n, then our derivative, df dx, is equal to the derivative of x to the power of n with respect to x. And that's equal to nx, where x is raised to the power of n minus 1. Now down below in this table here, we see some examples of different functions and their corresponding derivative, df dx, that goes with each function. So first of all, our f of x is equal to x, and our derivative, df dx, is equal to 1 from the power rule. For our second function, f of x is equal to x squared, and our derivative, df dx, is equal to 2x. So if we look at the function f of x is equal to x squared in a little bit more detail, what we've got here is x raised to the power of n, where n is equal to 2. So if we go to apply our power rule, our derivative df dx is equal to nx, where x is raised to the power of n minus 1. Now in this case, our value of n is equal to 2. So our derivative, df dx, is equal to nx, which is equal to 2x, where x is raised to the power of n minus 1, which for n equals 2, it's 2 minus 1, which is equal to 1. So our derivative, df dx, is equal to 2x to the power of 1, so our derivative is equal to 2x. So you can see here that by using the power rule, we can calculate the derivative of our function f of x is equal to x squared. We can do it quite quickly. And when we compare it to earlier in our video where we calculated the derivative of x squared using the definition of derivative and evaluating out the limits, it took a lot more steps. We worked out what f of x was and f of x plus h. We evaluated our difference quotient and we simplified it, and then we evaluated the limit. Whereas here, we've been able to do it very quickly. In fact, it can be done in your head. So So it's a lot less time consuming in this case to use the calculation rule. So we got another example of a function, f of x is equal to x cubed. So our derivative, df dx, is equal to 3x squared using the power rule. And for another function, f of x is equal to x to the power of 4, using the same line of thinking and the same rule, our derivative, df dx, is equal to 4x cubed. So our third calculation rule is the constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative of cu with respect to x is equal to the constant c multiplied by du dx, or the derivative of u with respect to x. For example, say we want to find the derivative of y equals 4x squared. We let x squared equal u, a function of x, and we let 4 equals c, a constant. So our derivative, dy dx, is equal to the derivative of 4x squared with respect to x. We apply our constant multiple rule, and we see that our derivative is equal to the constant c multiplied by du dx. So our constant c is equal to 4 multiplied by du dx. U is equal to x squared, and the derivative of x squared du dx is equal to 2x. So our derivative dy dx, being equal to c du dx, is equal to 4 by 2x, which is equal to 8x. So our fourth rule is the sum rule. If u and v are differentiable functions of x, then their sum, u plus v, is differentiable at every point where u and v are both differentiable. And at these points, the derivative of u plus v with respect to x is equal to du dx, the derivative of u with respect to x, plus dv dx, the derivative of v with respect to x. For example, we want to find the derivative of y equals x cubed plus 8x. Here we let u equals x cubed and v equals 8x. So our derivative, dy dx, is equal to the derivative of u, which is equal to x cubed with respect to dx, plus the derivative of v, which is equal to 8x with respect to dx. So our derivative dy dx is equal to 3x squared plus 8. So our fifth rule is the difference rule. The derivative of a difference of differentiable functions is equal to the difference of their derivatives. The derivative of u minus v with respect to x is equal to du dx, the derivative of u with respect to x, minus dv dx, the derivative of v with respect to x. For example, we want to find the derivative of y equals x squared minus 3x. Here we let u equals x squared and v equals 3x. Our derivative dy dx equals the derivative of x squared with respect to x minus the derivative of 3x with respect to x. And that evaluates out to be equal to 2x minus 3. So we can combine the differentiation rules to evaluate more complex polynomial functions. For example, say we want to find the derivative of y equals 2x cubed minus x squared plus 4x plus 5. So we can evaluate that by using multiple rules. We can use the power rule, the sum rule, the difference rule, the constant rule, and the constant multiple rule. And when we apply those rules to each area that they are relevant to in that polynomial function, we get the following. The derivative dy dx is equal to the derivative of 2x cubed with respect to x minus the derivative of x squared with respect to x plus the derivative of 4x with respect to x plus the derivative of 5 with respect to x. And when we evaluate that out, we get the derivative dy dx is equal to 6x squared minus 2x plus 4 plus 0, which is equal to 6x squared minus 2x plus 4. So it'd be far more time consuming to calculate the above derivative by evaluating limits. We'd have to evaluate our f of x and f of x plus h. We'd have to evaluate our difference quotient. We have to simplify it, and then we'd have to evaluate the limit as h approaches 0. Whereas here, by applying the relevant differentiation and calculation rules, we've calculated the derivative in just 3 lines. So the differentiation rules that we've covered so far are the first rule for derivatives of constants, the power rule, the constant multiple rule, the sum rule, and the difference rule. So I'm going to pause here, and our next video is going to cover some more differentiation rules. I'd just like to note as well that there are mathematical proofs regarding the validity of using each of these rules. Thank you for your time and for viewing this video, and I'll see you at the next video.